Hey kiddos, happy week 4. Today we are going to debrief the light bulb lab and start defining some of the patterns that we see in series and parallel circuits. So this lesson is going to be the same as the one that we did live in class. There may be some additional information. Okay, and so I'll make sure that that's clear in class if you're able to attend what will also be covered in this video that we didn't make it to in class. All right, if you can have this window open plus your light bulb lab, that will help you follow along and get your notes in your light bulb lab to have an efficient use of time. Okay, all right, here we go. All right, so today's goals are to experimentally derive the relationships governing voltage, current, resistance in parallel and series circuits. We'll also discuss in this video power in circuits, resistors and resistivity, and an idea called electron drift speed. The bottom 3 points are ones that I don't predict that we'll have time to cover in class. All right. So you guys took some data and I asked you to make a sketch or to have a screenshot of the circuit that you put together. So I'll draw a sketch. I think a lot of you have screenshots that you've created. And then we'll draw what's officially a circuit diagram. Okay. So if you had a sketch, you might have like a power supply or a battery drawn. You'll have a negative and a positive terminal. We'll say PS for power supply. Okay, and then you'll have some wires. Okay, officially, in your simulation, you were able to measure current just using a sensor. Okay. In the real world, we have to have an ammeter, a device that is in a circuit so that electrons can flow through it, okay, to measure current. And so I'm just going to make that a circle with an A. This is a sketch still. And so let's say we have 2 light bulbs in series. Okay, and I'll draw light coming off of them because they're light bulbs, obviously. And then we'll go around like this. Okay, so those are all attached. You measured the voltage across the power supply, and that voltmeter wasn't in the circuit, right? You were able to make a measurement with the voltmeter and take it out of the circuit. Electrons weren't traveling through, so I'm not having these guys connected just to show that it's not part of the circuit. And then I asked you to measure the voltage across each light bulb. So you could do something like that. Now, what about an official circuit diagram? So circuit diagrams, even though the word circuit really means circle, we've got a circuit diagram is like rectangular. They're nice kind of square 90-degree edges. And so when we draw a power supply, you will see they'll be square. The official circuit diagram circuit will be square, and power supplies are drawn as a short line and a long line, or a series of a couple short and long lines. That's a power supply. All right. And so I'm just going to draw one long and one short, but if you see more than one, that's usually just like there are 2 batteries put together or something like that. So the small line looks kind of like a negative sign. And the small line is considered by convention the negative side of the power supply. And the long side is considered the positive side of the power supply. All right. And then I have my ammeter. This circle with an A in it is the official abbreviation for ammeter, the thing that measures current. Okay, and then typically light bulbs have X's in them. Sometimes you might see a symbol, like this is a light bulb. I think sometimes you might see a symbol that looks like that to kind of mimic a resistor. I typically draw a symbol with an X. Okay, so we've got our 2 light bulbs, and then we go back around. See, similar, but squared off with some official symbols. Also, you can draw a voltmeter, right? Just like we did, except everything is squared off. Okay, and that is not touching. Okay, so we've got our circuit diagram and our sketch for our 2 light bulb series circuit. All right, so it's your job to make those sketches in your light bulb lab document. To make those circuit diagrams for each of your 3 sketches or screenshots for series and parallel circuits. All right, let's look at parallel. Parallel, our sketch would look something like so. We'd have our ammeter, and then we'd have a little junction with our light bulb, and then another light bulb, and then they would kind of like join at a spot and do that sort of business there. Okay, voltmeter, right? And then I'll draw a voltmeter down here. All right. So this voltmeter isn't in parallel with the 2 light bulbs. It's just measuring the potential difference across that 1 light bulb there. Okay, so if we were to draw this in a circuit diagram, this side's negative, this side's positive, it'd be squared off, and I actually want to draw my ammeter here, and then I would do this sort of thing where I'd make a junction, that's supposed to be a dot, and then I would have my light bulb here, whoops, and a light bulb here. Right, so this is all squared off, and then a junction kind of in the middle where they connect, and then you'd bring it back around, and you still would have your voltmeter, okay, here, and your voltmeter there. Okay, so again, that's how you would draw a parallel 2 light bulb parallel circuit in a circuit diagram format. Okay. All right. So the data that we collected was voltage and current. You also wrote down the resistance of your light bulb. Okay, and we're going to walk through conceptually what each of those things is. In the previous lesson, we defined current, right, as charge flow rate. We know that voltage is related to, or voltage or potential difference is related to the amount of energy, right, that electrons have. Resistance is the last concept that we need to talk about. And I like to think of resistance as electrical friction. Okay, so electrical friction resistance is a property of a wire or a device that we put in a circuit. The resistance resists the flow of charge. Okay, and it slows it. Right, and just like friction in like a macro world like we studied last year, electrical friction also reduces heat, right? So resistance produces heat. Resistance can be provided by devices, right? Like light bulbs. Any appliances, like your cell phone that you plug into a wire, that acts as a resistor in the circuit. So appliances, or they're actual little devices called a resistor, where they might not need something at that point in the circuit to accomplish a task, like light a light bulb or charge a cell phone or something. They just need to slow down the charge, and so you can put in a resistor. All right, where does that energy go? It goes the energy dissipated by a resistor goes into light, appliance motion, like running a fan or something like that, or just heat. Okay. Resistance has an abbreviation, which is capital R, and its unit is the ohm. Okay, it's written like the Greek letter omega. Okay, and it's pronounced ohm. All right. Okay. Now, I mentioned previously that resistance is a property of a material. You can imagine that plastic would have a different resistance to electrical flow than lead or copper or gold. All right, so resistance, here's our resistance here, capital R. It has to do with three factors. Okay, resistance in ohms has to do with resistivity. Resistivity is a property of materials. It's abbreviated with the Greek letter rho. It looks like a lowercase p, but it's the Greek letter rho. In ohm meters, it's a property of a material, right? So each material, like the metals we usually use in circuits, gold, copper, steel, they each have a different resistivity. Okay. It also depends on the wire length. Okay, so the longer a wire is, the more resistance it will have. And cross-sectional area, right? The area, if you're to take a wire and slice it, right? The cross-sectional area is the area of the circle that you would see at the end of the wire when you slice it. Okay, so it really is how fat the wire is. And so we can see that resistance increases if the resistivity of a material is larger. Resistance increases the longer the wire is, and resistance decreases as the area, the cross-sectional area of the material increases. Okay, so resistance is directly proportional to resistivity and length, right? If there's a longer wire, electrons will be interacting with the electric field of charges in the material more, and that will slow down the flow of charge. The cross-sectional area, the fatter the wire is, will actually decrease the resistance. Okay. So let's talk about the patterns that you saw in your series circuit first, and we will do that in the next video.